All right, welcome back, everyone. In this section, we're going to talk about the graphs of the two types of functions you probably know the most about, which are lines and parabolas, or if you prefer, you could say linear functions and quadratic functions. So let's start with lines, which are probably the thing in your mathematical career that you've thought about the most. And so when you hear lines, you probably first think about this equation y equals mx plus b, which is the equation that we usually use for lines, and so we'll usually write them this way. And so in this particular equation, you'll remember that this m stands for the slope, and this b stands for the y-intercept. And I'll talk about exactly how to interpret these in a moment, but the y-intercept, you should already know from the last video what this is. And then this is the slope. You might wonder why m for slope. This is because the French word for slope is monter, which means to climb. And in particular, S is a letter that looks a lot like fives, so usually, when possible, we avoid using S for variable names. So if you've always wondered why M for slope, that's why. So what does the slope tell you? The slope tells you the rate of change. And we'll talk a lot about what this means as we go along. But for now, I just want to think about this in terms of the line that you get. So if I get a line like this, the y-intercept is telling me where this intersection is, that is, where the y-intercept of the graph is. And then the slope is telling me something about the steepness of this line. And so big slope means very steep. Okay. And then small slope means not very steep, or very shallow, if you want. Okay. So here's a line, big slope, that's very steep. And here's a line with a shallow slope. So, or a small slope, if you want. And so that's part of the information that's contained in the slope, namely how the line slants, and if it slants very steeply or very shallowly. The other thing that's baked into the slope is whether it is positive or negative. And so every line I've drawn so far has a positive slope. And so positive means, and so people like to say that this leans to the right, but basically positive means the line leans that direction, whatever you want to call that, and then negative means the line leans the other way. So positive means it leans that way, negative slope means that the line leans the other way, so something like that. But all of this stays true either way. So a very big negative slope will mean it's very steep, but leans in this direction, and a small negative slope will mean it's very shallow, but leans in this direction versus that direction. I also did not talk about what happens when the slope is 0. Okay. And so 0 slope corresponds to a line that is horizontal. If you have trouble remembering which is horizontal and which is vertical, a horizontal line is one that goes like the horizon. That is where we're connecting this. Now I want to jump back to this connection between slope and change. And so when I say that slope is connected to change, it's really telling you about the change in the output. And really per change in the input, but for the moment, let's focus on the numerator here. Let's focus on the change in the output. Zero slope tells you, how does the output change? It doesn't. Positive slope tells you, how does the output change? It gets bigger. The output here, remember that's the y coordinate. As I move from left to right, the output is getting bigger. Whereas negative slope tells me, how does the output change? It tells me it gets smaller. And so really the slope is telling me, first off, does the output get bigger, smaller, or stay the same? And that comes from the sign of the slope. That is just whether it is positive, negative, or zero. And so that's the first piece of information, again, that you can think of the slope as giving you, is what's happening to the output, how it changes, and that's corresponding to the numerator here of this fraction that I've written here. But once it's told you that, it then also tells you how fast. Okay. If the output gets bigger, how quickly does the output get bigger? And so, again, big slope, that's telling me that the output gets bigger very fast, or gets smaller very fast if it's a big negative slope. And the reason why we have this change in the input piece here in the denominator of the slope is that we really need to decide, how does the output change as the input changes, in order to make sense of the question, how fast does this function increase? And so if I draw you two lines, one steep, one not so steep, the way the slope ultimately gets at the fact that this line is steeper than this one is to say, okay, let's clip the same points here. There's 2, there's 4, the output there is 0, the output here is whatever it is. And then I can measure 2 here and 4 here. And then the reason why this line is steeper than this line is that if I look at how much the output changed from the interval 2 to 4, it's that much if I carry this over on this line. So it is that much change if I carry it over on this line, whereas it's only this little bitty bit of change if I look at it over on this line. And so that's telling me how much output there is, but I need to decide how much I'm changing the input to see how much that changed. And so in this case, changing the input by 2, in both of these cases, change the output by differing amounts. Okay. You don't have to think about all of this too much. Just remember that when you're calculating a slope, you always calculate it as a change in output over a change in input. Now, there's one more slope, even though you'd think I'd covered them all, because I've covered positive, negative, or zero slope, but we also have lines of undefined slope. And our lines of undefined slope are always vertical. And there's a couple weird things about this, other than just that the slope is undefined. Okay. One is, if I picture my favorite vertical line, I don't know what your favorite vertical line is, but there's my favorite vertical line for today. This is not the graph of a function. Why is that? Well, if you think back to how you decided graphs were functions in high school, you used something called the vertical line test. That is, you looked for every vertical line through the graph and made sure that there was no vertical line through the graph that hit the graph at more than one point. Unfortunately, given that this graph itself is a vertical line, on this vertical line it hits the graph at infinitely many points. So that tells us, hey, this thing's not the graph of a function. Also annoyingly, this graph is not of the form y equals mx plus b. In fact, actually, you probably know that it can't be of the form y equals mx plus b, because if it doesn't have a slope, well, then how am I possibly going to fill in this m here? Okay. And so vertical lines actually have a different formula for how we write them. Okay. Namely, let's say this point here is 3, 0. The fact that this line is vertical, what that's really telling me is every point on this line looks like 3, something. And so there's a really easy way to define what all of these points have in common. Namely, what all of these points have in common is they all have the x-coordinate 3. And so the equation of this line is just x equals 3. And that's how we'll write it. Now, because vertical lines don't correspond to graphs of functions, we're not going to see them all that often. But a place we'll often see them, and you've probably seen this before, is in the context of talking about what are called vertical asymptotes, which we'll talk about later in the course. But if you picture your favorite graph of some sort of fraction, you might picture something that looks something like this, where sort of this function spikes off to infinity or negative infinity at this point. This vertical asymptote is also a vertical line. And so when I try to describe this, or when we describe this later, our equations are always going to look like this. X equals something. Either x equals 3, x equals pi, x equals -7, whatever. It'll always end up having an equation that looks like x equals something. And so we'll write those down a number of times later. Okay, I'm going to wrap up this video here for now. In the next video, I'll just do a few examples to remind you of, hey, how do you do all of these questions where they give you some information about a line and ask you what the equation of the line is? Probably you've seen these a lot, and so you probably just need a brief refresher to remember how these sorts of questions work. But until then, I'll see you in the next video.